Hey there, everyone. So, I realized at the end of last video that I forgot to mention something rather important. Okay, so this should be the ending screen of the last video. All right, so in this diagram, right, we talked about the angular momentum as measured from two different points, right? Point Q and point C here at the center. As the Earth rotates or revolves around the Sun, as measured from point Q, the angular momentum changes, right? That's because the distance from point Q is always changing. Either it's increasing or decreasing. However, the angular momentum as measured from the very center at point C as the Earth moves around is always the same, right? The angle is always 90. The speed is always the same, more or less, and the distance r is always the same. So down here, angular momentum L sub c, I'm going to write over here on this page because I have much more room. So that was equal to r cross p, right? Or rather r from point C. Now, the magnitude of each of those vectors, that's just r, mv sine, in this case, 90, but that's 1. Now, this is r mv, right? We can write v, where is it? We can write v in slightly different terms, can't we? Right? Yes, we can. We can write v as omega times r, right? That comes from the relationship between the linear speed and the angular speed, right? Omega, not w, right? So recombining, we have m r squared times omega, okay? Now, does this look familiar at all? Mass times a distance squared. You may recognize that as the moment of inertia. Okay, so let's take another look back at this orbit now. So that means the mass is the mass of the Earth in this case, and r is the constant distance of Earth's orbit. Okay, and that won't change. Omega won't change either. So this is an example for two discrete objects. In other words, two independent, two separate objects. But what if I have a solid object, like a ball turning, right? What if it's just the Earth rotating about its own axis? If I had that, right, and it's rotating with some omega, we have all of these different points in here, right? All of these different tiny bits of mass, if you will, and they're each a different distance from the center, right? Or rather, they're each a different distance from the axis. Okay, so we can write this, for example, as this. We have each of these tiny bits of mass. I'm going to call them m sub I. Each of these tiny chunks. And they're all a different distance, which I'll call r sub I, from the rotational axis. Okay, wherever these masses are, wherever these chunks are, they all have their own respective distance from the rotational axis. And so we can amend this equation to now account for an object with a lot of, well, a continuous mass, right? Not just 2 points. So now the angular momentum from the center we need to treat as a sum. Okay, and I'm going to pull actually the omega outside of that sum, and we can write it like this. So this says, for every mass, right, for all, say, I masses, they're each their own distance from the central rotational axis, C. Okay, so if we add all of those up, we get that object's moment of inertia, which we know as I. Now, omega will be the exact same value for each of these masses, regardless of where they are, right? That assumes, of course, that this object as a whole is a rigid object. In other words, there's no differential rotation, meaning some parts don't rotate slower than other parts, right? They all rotate about this axis at the same rate, right? That's what omega says. And so this expression now, the angular momentum about the center, or more specifically the center of mass of an object, is simply equal to I omega. Okay? So this is incredibly handy about center of mass, because it'll come up in later examples. But we can use this expression in conjunction with, what's it back here? With this expression as well, right? They're both equal to the angular momentum, but this case, right, is specifically for an object simply moving with respect to some random point in space, right? And again, this is for just a single object. The difference here is that this is a continuous mass object, right? It's acting as one. So if it's rotating about its center of mass, this is how we write the angular momentum, okay? You can turn this into a vector if you want, right? Vector. And in this case, the omega will be a vector, and you can tell which way it's going by using your right hand. Right, so the right hand rule says if you take your right hand and you curl your fingers, your forefingers, right, your pointer, middle, ring finger, and pinky, in the direction of omega, so around the axis, your thumb will extend in the direction of the angular momentum. So in this case, L would point up the axis, if you use your right hand. So the same thing applies for torque, right? As does angular momentum. All right. So thanks for watching.